Good afternoon, everybody. Welcome to UCL's Lunch Hour Lectures. It's nice to see so many people here today, and I'm very pleased to introduce today's lecture, which will be by Professor Andrew Coates, Life in Our Solar System, Redefining the Habitable Zone. Our speaker today, Andrew Coates, gained a BSc in Physics from UMIST in 1978 and an MSc 1979 and DPhil 1982 in Plasma Physics from Oxford University. He has been at UCL's Mullard Space Science Laboratory, also known as Department of Space and Climate Physics, since 1982, with temporary guest positions at Max Planck Institute for Solar System Physics in Germany, University of Delaware in the USA, and the BBC World Service on a media fellowship. He's now Deputy Director for the Solar System at UCL MSSL. His space mission involvements include the ExoMars 2020 rover, where he leads the Pancam team, Cassini, where he led the electron spectrometer team, part of the Cassini plasma spectrometer, Cassini which recently dived into Saturn, as you may have seen on the news, Venus Express, Mars Express, and the Giotto mission to Halley's Comet. His scientific interests include the solar wind interaction with planets and comets, space instrumentation, and he's authored and co-authored over 500 publications, including 380 refereed. He's very active in space and science outreach. And I now invite Andrew to begin his lecture.
Well, thank you very much, Andrew. Yes, and it's great to see such a good audience here. So I'm going to be talking to you today about life in the solar system and redefining the habitable zone. And I'm from Mullard Space Science Lab, part of UCL. So we're out in Surrey. We're a department out there. Andrew's the head of the department. And about 199 people working on space science and engineering out in MSSL. So this is UCL's space department. So, and the website is there. So on the left-hand side here, you can see a picture of the ExoMars rover. This is going to Mars in 2020. And on the right-hand side, this is the JUICE mission, which is going to go to Jupiter and its moons, being launched in 2022. And we'll get to talking about that. But to start off with, redefining the habitable zone. So we've got to start off with actually what is the definition of a habitable zone. So there's something called a circumstellar habitable zone. So this is the habitable zone around a particular star, or the Goldilocks zone, as some people call it, where the conditions are just right. So it's a region in which a terrestrial mass planet with favorable atmospheric conditions can sustain liquid water on its surface. So that's the sort of traditional definition of a habitable zone. And of course, the Earth here, you can see the picture of that, is a great example, our great example where we only know of life on Earth. We don't know of life anywhere else in the universe yet, but we're searching, and the habitable zone is one of the things which we consider in doing that. Now, the second slide takes a moment to explain, but this shows the radius of the orbit of a planet relative to the Earth. And on the axis going up here are different types of stars. So if we start right in the middle here with the Sun, so this is what's shown is the mass of the star relative to the Sun. So if we start with the Sun, and we can see the planets here going out from Mercury, Venus, the Earth and Mars, and then of course the outer planets there, Jupiter and Saturn and so on. And of course, over the top of that is plotted in blue the habitable zone. So we can see the habitable zone going across here. So of course the Earth is within the habitable zone. This is where we know there's life, and this is the place at the moment where the interest starts, of course. Now the habitable zone doesn't at the moment extend to Mars, and it doesn't extend to Venus, but conditions used to be different on those, and so at least with Mars, we think that the habitable zone may have extended there before. But one thing that's been discovered on Earth in recent years is subsurface habitats. And so that's shown in the inset here, where below the surface of the Earth, in black smokers underneath the ocean, we can find different types of life, extreme types of life, which we hadn't known existed until maybe 10, 15 years ago. And so that makes us sort of start to think of life in a different way. So the habitable zone, the traditional habitable zone, is there. So Mars seems like a good place to start in terms of looking for life. Venus, conditions are not right, it's much too hot, and a runaway greenhouse effect. But Mars could be a potential possibility. So we'll start with that. So actually Mars 3.8 billion years ago is quite different from what Mars is like now. So 3.8 billion years ago, there was water on the surface, there was a climate which was able to support that, liquid water on the surface of Mars. So some of the evidence from that is from the orbiter missions which have been around Mars. This is one example from the European Space Agency's Mars Express mission, showing one of the regions on Mars which was carved by water 3.8 billion years ago. Bear in mind, the whole solar system is 4.6 billion years old. So this is a long time ago in the solar system's history. So very early in the solar system's history. Actually, at about the same time that life was developing on Earth, Mars had about the right conditions in terms of the water on the surface. The other thing that Mars had at that time is a magnetic field. This diagram shows basically a map of Mars. The colors on it show the altitudes on the Martian surface, going from white and red, which are relatively high, to blue, which is relatively low. And you can see in the southern regions of Mars, that's where we get the southern highlands region of Mars here, the northern region relatively low. But plotted over at the top of that are some white and black lines, and those show the magnetic field of Mars, measured by an orbiter a few years ago now. So back in 2001, this paper was published. And that showed that these are actually crustal magnetic fields. They're left over from a time when Mars itself used to have a magnetic field. The Earth, of course, does have a magnetic field now. It's one of the things that cradled life starting here and continues to do that, protecting it from the solar wind and from galactic cosmic rays and so on. Mars used to have a magnetic field, and this was the first evidence for that. Mars also used to have rampant volcanism, and this is the largest volcano in the solar system, which is Olympus Mons on Mars, and that particular volcano is about 600 kilometers in diameter. So Mars was volcanic, it had a magnetic field, it was very Earth-like in its climate, and so we think that 3.8 billion years ago is a good time for life to have developed on Mars, about the same time as it was developing on the Earth. So Mars now is very different. The volcanoes are extinct, there's no large-scale magnetic field, there's only the remnant regions of magnetic field, or crustal magnetic fields, which are left. There's a very thin atmosphere. All that has been pulled away over the 3.8 billion years by the solar wind. So Mars lost its magnetic field about 3.8 billion years ago. It seems there was a large collision which actually caused that to happen. Okay, and now it's cold and dry. So we think that there could have been life on Mars. And so what do we need for life? And so I've put down here some of the requirements for life. What do you actually need? So we need liquid water. So that's one of the things we talked about with a habitable zone. We need the essential elements which drives life on Earth. So carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And we need a source of heat, and we need long enough for life to develop. So that's the sort of recipe for life. And we think that could have been there on Mars 3.8 billion years ago, which is why the excitement is there for looking at that. So one of the ways we're going to be looking at Mars is with the ExoMars 2020 rover. And this is a model, computer model of the rover showing the panoramic camera system at the top of the mast. I'll talk about that a little bit more in a minute. This is the rover itself. At the back of the rover, there is a subsurface sounding radar. At the front of the rover, there is a drill. And so with this mission, we're going to, for the first time, drill significantly underneath the surface of Mars. This will be able to drill up to 2 meters underneath the surface. The surface of Mars is now very hostile to life. It's as well as being cold and dry, it's got a relatively high radiation environment, it's got a high amount of ultraviolet radiation coming through, its thin atmosphere, which is less than 1% of the Earth's atmospheric pressure. So this rover needs to drill up to 2 meters underneath the surface, and that's what we'll be doing. So this is much further than people have drilled underneath the surface before. The Curiosity rover, which NASA has on Mars at the moment, for example, can drill 5 centimeters. So we're drilling 2 meters, so it's 40 times as deep, to get below this region where we need to get to actually be able to look for life. And so the rover will do that. And so the payload which is on the rover is shown here. This is quite complicated, but if you notice the UK flag at the top left-hand corner of the Union Jack, this is what we lead. So this is the Pancam system, the panoramic camera. On the left-hand side, the instruments are basically setting the context for the drilling experiments. On the right-hand side, those instruments are inside the rover and will analyze samples which are collected from the drill. So the drill drills down, gets a sample, and brings it back into the analytical drawer. And so we will analyze those to look for signs of life. And this actually has the best chance of any mission which is selected at the moment in terms of actually detecting the signs of life and habitable type of conditions, but also signs of life, molecular signs of life on Mars. And we think that would have been there 3.8 billion years ago. So our part of this at UCL, funded by the UK Space Agency, is actually the panoramic camera system. So this is the eyes of the rover, the scientific eyes of the rover. So on the right-hand side, this is the optical bench, which sits at the top of that mast. And I brought here a model, actually, of the optical bench. This is a scale model, one-to-one scale model. This is what we're building at the moment, and it stands about that high above the surface on Mars. So if you imagine me being the rover, and then we'll be able to look around and look for places to drill. So we've packed as much science as we can into what is basically a camera system. So each camera, there are 11 filters on each of the on each of the two cameras, one at each side. And also you'll notice there are two wide-angle cameras. They're separated there by 50 centimeters. So imagine that sort of above there somewhere. We can get better stereo reconstruction than we can do with the human eyes with that system. And we pack the science into it in terms of getting the geological science. So using filters, we're looking at parts or colors of light in order to look at the composition of the surface, and so seeing basically where to drill. So we also have a high-resolution camera and calibration targets and so on to help us make the right measurements. So this is a very exciting mission. It's something which UCL is leading. So I'm the principal investigator for this. My project manager is Mary Carter, and this is the UK involvement. And in fact, there's a big UK team involved in this as well as us here at UCL, but we're actually leading this. There's an international science team. There's the hardware team includes Germany and Switzerland. Austria are involved in doing the 3D imagery, and also Wales. So University of Aberystwyth are involved in the small items. So we have a very key role in the mission as a whole. Okay, so we've talked about Mars and how we're going to look for life on Mars in the future. So on now to Jupiter and the Galilean satellites. So in redefining the habitable zone, we're now sort of taking things out into the solar system to look at the moons around Jupiter and Saturn. So in particular, we have Io here, Europa, Ganymede and Callisto. So of these, Europa, Ganymede and Callisto are really good targets because they have subsurface water oceans. Io is volcanic. It's more volcanic than the Earth. It produces a large amount of material, 1 ton per second of material, which spews into the Jupiter system. So amazing volcanoes, but it's not water. The other three have water underneath their surface, and that's been found by a number of techniques. So looking at the surface, it's a very young surface. It's sort of recycled and refrozen every now and then. There are streaks on it, you can see, up from this subsurface water ocean, and that brings material to the surface, and then we have the young surface then. Okay, so the Galileo mission, the NASA Galileo mission in the 1990s, found basically that we have these liquid water oceans underneath an icy crust. The way it did that was with a magnetometer, so it's by measuring the magnetic field and also with plasma instruments to make sure it wasn't a contamination due to material coming off the surface and becoming charged. But it was able to, looking at the signatures as basically the spacecraft passed these objects, you could work out models which show that the magnetic field signature is consistent with a conducting ocean, and not only that, probably a salty ocean underneath the surface, and that's the case at Europa and at Callisto. At Ganymede, that's the case as well, but Ganymede also has its own magnetic field, and so this is unique in the solar system moons. It actually has its own magnetic field, Ganymede, and this is going to be the target of the JUICE mission being launched in 2022. So also these objects have weak oxygen and water atmospheres. So Ganymede and Europa sit basically in Jupiter's magnetic field, and so this is an illustration of Jupiter's magnetic field and the radiation belts of Jupiter, and those are energetic particles which hit the surface and drive off oxygen and, well, water really from the surface, from these frozen icy moons to produce very weak atmospheres. And as I say, Ganymede is unique in that it has a magnetic field. So that's a little bit, as I say, remnant of the Earth. So we're sort of pushing outwards in terms of where the habitable zone could be. Now, at Europa, the interior structure of that is very interesting. So based on models, it looks like at Europa, uniquely in the Jupiter system, that liquid water ocean, there from the magnetometer data, seems to be in contact with silicates or sand. So the other moons, Ganymede and Callisto, don't have that. But at Europa, this ocean is in contact with silicates, and that means that this moon in particular has the best possible chance for life developing there. And so this is pushing the habitable zone out into the solar system. This is another artist's impression. We don't really know how deep the water ocean is on Europa, and what we want to do with the JUICE mission and with NASA's Europa Clipper is to actually look for the depth of that ocean. So how do we know about this? How do we know about interior structure? So there are a few things that we can do. We can make gravity measurements as a spacecraft passes one of these moons. We can use ground-penetrating radar from the spacecraft to look underneath the surface. We can look at radar data to look at the body's shape and see that as it flexes, as it goes around its parent object. We can look at the magnetic field and the plasma interaction. As I say, that's what was done with Galileo to actually find that those had subsurface oceans. And we can, in the future maybe, even have seismometers on the surface of these. That would be great, wouldn't it, to actually have something on the surface listening to the cracking of the ice as it goes round its parent object. But these are the techniques which can be used, and so most of these, all except the last one, are actually going to be used on the JUICE mission in a few years' time. So JUICE, I was lucky enough to be on the science definition team for this, and this came up with the assessment study report. This got selected as the next large mission for the European Space Agency, so this is the other big mission involvement which I'm talking about today. It launches in 2022, it gets to Jupiter in 2030, and it goes into orbit around Ganymede in 2032. So some of the younger members of the audience hopefully might be able to actually work on this once it gets there, and certainly my younger colleagues will be the ones leading the instrument at that time. So Geraint Jones at NSSL is actually the lead for our part of this, which is going to be part of the plasma instrument for JUICE. Okay, so on to Saturn. So Saturn, another fascinating target, and of course the Cassini mission, which Andrew mentioned in the introduction. We were lucky enough to be involved with that as well. And this is one of the really iconic images from the Cassini mission. So we can see Saturn being, effectively in eclipse, looking at it from further away from the sun than Saturn. So looking at the other side towards the sun, and you see the ring system lighting up. So fantastic image. The orbit at 4 Saturn radii is actually the orbit of Enceladus, and that's where this big dust ring has its source. Saturn with its rings is shown here in beautiful relief like that. We can see in this image Mars and Venus, and we can also actually see the Earth and the Moon. There's just one pixel where you can actually see that. So looking back at our own object in this type of image is just stunning. And actually, the day this particular image was taken, we all went out and waved to the spacecraft. You can't actually see us because it's all in one pixel, but nevertheless, I took the kids out and actually did that. Okay, so Saturn's moons, what have they told us about habitability? So there's Titan and Enceladus, which Titan is at the top. This is an image showing effectively down to the surface of Titan. So Cassini, of course, was the orbiter, but it also had the Huygens probe associated with it, which actually landed on the surface of Titan as well. And the image on the right shows the haze in Titan's atmosphere. And then at the bottom, we have Enceladus, which is a relatively small moon orbiting at that distance, about 4 Saturn radii away from Saturn. And here are some other images showing one of the remarkable discoveries of the Cassini mission, which was the plume of Enceladus. So Enceladus is spewing out water at a relatively high rate, maybe about 1/10 of the rate of Io's, so it's about 100 kilograms per second, something like that, of material which is coming out of Io. in these plumes, and you can see these wonderful images of the plumes. And it was actually the magnetometer which discovered the plumes in the first case, but everybody else went back and looked, and you can see that in the data, so a remarkable discovery. But Titan and Enceladus are both potential places which are interesting. So with Titan, people had thought that this might be a really good location for life, because actually before the Cassini mission, we had the Voyager mission, which flew past the Saturn system and took images a bit like the top left. This is actually a Cassini image, but this is what you get in the visible. But if you then use other wavelengths, the infrared and ultraviolet, you can actually see down to the surface. And so Voyager didn't have that, so one of the big contributions of Cassini was to be able to do that. So the top right-hand two images are using a combination of ultraviolet and infrared, and you can see down to the surface, and the surface is, the dark regions of the surface show signs where there are lakes, but it's lakes not of water as we know it. This is of liquid methane and ethane. So the temperature of that surface is very low at minus 180 degrees centigrade, and that is near the triple point, as it's called, of methane. So the Earth's surface is near the triple point of water, and so this is why, you know, we depend on water for our conditions. But at Titan, on the surface at least, is methane. Underneath the surface, though, there is a subsurface water ocean underneath Titan's surface. And there's another thing, in the atmosphere of Titan, one thing we discovered, this is a complicated diagram, but the central part just shows you the interaction of sunlight and energetic particles with the nitrogen and methane atmosphere that Titan has. Titan is the only moon in the solar system with a significant atmosphere, and it's nitrogen and methane. This is a bit like the Earth's early atmosphere. And we have different chemical pathways which are driven down to eventually form the haze. And so what we've seen with Cassini is on the top left we can see the neutral particles. This is the positive ions. But with our instrument from part of UCL, we actually discovered heavy negative ions, which are very important in terms of prebiotic chemistry going on in that atmosphere. So very interesting. And we recently had a student working on this, Ravi Desai, who's just finishing his PhD at the moment, working with us on that discovery and providing some important new analysis. Okay, so Enceladus, though, is the other place where there could be life in the solar system. So Enceladus, again, this is a picture of the plumes here. There's water coming out of the plumes. I love the bottom left image because that shows the culprit for forming those rings. And so this is Enceladus pushing all this material out into the region near to Saturn. And you can see there it is, the sort of slightly brighter part here. That's Enceladus producing material which then goes out and forms that E-ring, as it's called, of Saturn. And so Enceladus is definitely the culprit, and that fills the inner region near to Saturn with that. So you get the idea about water with this next image. This is another thing called Enceladus, which is actually in Versailles. So I was lucky enough to see that at a time when it was on. So I thought I'd take a picture of it, and there it is. So this shows you. But this is puny. This is a very small amount of water compared to the water that we actually get out of these plumes at Enceladus, and these are going off into space, and we can fly through that and actually sample that subsurface ocean directly in those plumes. So that's a very exciting set of measurements. Okay, so Enceladus, this is the image. So the plumes are actually coming from what's called the tiger stripes, which are these things at the bottom left here, the sort of relatively blue regions. This is a color-enhanced picture, but it shows you basically streaks on the surface, and there's a very complex source of the material there. But this is, and this is the image I showed earlier, but I wanted to mention that there's not only the detection of the plumes, but also some other things which give us clues to habitability here. So first of all, sodium was detected directly in the dust, or the ice coming out. This is very important in terms of it could be a salty ocean. There's silicates, i.e. sand. So this is indicating that there could be subsurface vents, a little bit like those vents on Earth, which where extremophile life can happen. And then very recently, just this year, the iron and neutral mass spectrometer instrument detected hydrogen in the plumes of Enceladus. Now this is very interesting because of course hydrogen is one of those things needed for habitability. And so that means that, Enceladus becomes a really interesting habitable type of environment. And also in the Saturn system, the other place for habitability is Titan, where we have prebiotic chemistry going on. So this is just an image showing how the salt grains were discovered. I won't go into detail about that. But what I will do is show what a sort of holiday snap might be, or a sort of advert for a holiday on Titan. So it says, for those of you who can't see this, it says, "Ride the tides through the throat of Kraken." And so this gives you, that's one of the lakes on Titan. So it's a beautiful image from JPL. Another one to do with Enceladus. So holiday plans now, and then you can make your plans later on. Of course, you know, the whole question of human spaceflight and whether it can really do that is another lecture. But so finishing now, we're looking at missions looking at habitability in the future. So we have the European Space Agency and Russia. ExoMars mission, that's the thing which our camera system is on, going in 2020. So that's launching in 2020 and gets there in 2021. So when we get there and start taking the images on the surface, that will be a UCL-led camera which is producing those images. So something to look forward to for the future. The JUICE mission on the top here, this is, as I say, launching in 2022 and gets to Jupiter in 2030, Ganymede orbit in 2032. NASA also have plans, and so they have plans for a Europa Clipper and for a Europa lander, although, well, I believe this one is approved, but this one is sort of waiting for potential approval. And so I'll just finish with sort of changing that picture a little bit to say that the habitable zone, we can redefine that to not only just include where we are now, the Earth, and where Mars was 3.8 billion years ago, but also these deep habitats out at the outer planet moons. And so this is the redefinition of the habitable zone that we talked about, the necessary ingredients for life, again, being water, the essential elements, energy and time. So we can see here, you know, the moons of Jupiter and the moons of Saturn in terms of redefining that habitable zone. And of course, we can go, we can sort of summarize that here, which is in a big, long table. The point of this is that Mars and Europa and Enceladus are probably good places to look for life, the signs of life. In the case of Mars, 3.8 billion years ago. In the case of Europa, possibly now even, and possibly now with Cassini. So, and Enceladus has really sort of shot up the ratings in terms of where there could potentially be life in the solar system, and this gives you a flavor of that. Just to go very briefly to extrasolar planets, and this is just one example of an extrasolar planet system, the TRAPPIST-1 system. So this is a star which is much smaller than the Sun. It's only 8% of the Sun. It's 39 light years away. But amazingly, it has 7 planets which could have water on the surface, of which are potentially have some of the aspects of habitability, but 3 of those in the habitable zone, as we would define it now, i.e. the one involving water. So this interesting set of discoveries was done with using transits of these of the star. Okay, so the last slide just sums up really. So habitable conditions really are what we would now say are the new habitable zone, if you like. And so where conditions are right for life, that's something which is of course important. We have liquid water and the essential elements and energy and time. So if we have all of those things, then these are habitable conditions and they're places where there could potentially be habitability. So the best bets in the solar system, obviously we know of life on Earth, but Mars 3.8 billion years ago, Europa, possibly even now. As I say, the reason for choosing Europa over the other moons of Jupiter is to do with the contact of the ocean with the silicates. And then Enceladus, which of course has jumped into this top categorization now. And then eventually Titan. Titan might actually be a tinderbox waiting to happen, because we can see signs of prebiotic chemistry going on now at Titan as well. And then again, it's a completely different talk, but extrasolar planets, that's another really good place to be looking for the habitable zone and try to understand where things are. So I'll stop at that point and see if there's any questions. Thanks very much.
Thank you very much, Andrew. So there is a little time if you have a few questions. If we do have questions, could we ask that you keep them short and wait until you have a roving microphone before you speak? So we had a hand up here, please.
Yeah, I was just wondering what kind of precautions are taken when you send out rovers, etc., so that, you know, if there is life, you don't contaminate or, you know, cause issues.
Yeah, it's a good question. So we have to be very careful about what's called planetary protection. So we're protecting Mars, as it were, from us, from taking terrestrial microbes. So we have to, with ExoMars in particular, we have very stringent conditions for actually cleaning the spacecraft, very importantly. And so that was a very key part of the mission design, to actually make sure it's cleaned. And so that what we do is what's called DHMR, which is direct heat microbial reduction. So we make sure all of the outside of the surfaces are actually cleaned and that we're not contaminating the measurements. I mean, ultimately with Mars, you'd like to send another spacecraft and perhaps bring a sample back. You know, that's the other way of doing it. But in terms of this mission in particular, where we could actually find life on Mars, yes, we have to be very careful about that. And actually with Cassini, at the very end of the Cassini mission, of course, that in September, that was deliberately plunged into the planet Saturn rather than potentially contaminating either Titan or Enceladus. Titan it had used for its orbital changes during the mission, 13 years at Saturn, and then Enceladus as well, avoiding that. So those are potentially astrobiologically interesting targets, and so we avoided it by actually deliberately crashing the spacecraft into Saturn. So for somebody like me who's worked on it, for since 1989 in my case, so a big part of my career was on Cassini. And so, there was something of a tear in the eye at the time that actually happened. But it's to do with planetary protection and making sure we don't contaminate measurements for the future.
Any more questions? Gentlemen.
Thank you. I was just wondering what propulsion drive that these craft use. I heard some time ago about a thing called an ion drive being used for long distance, but I didn't hear any more of it.
For some missions that is used. So the one that has recently been to an asteroid, for example, to Ceres and Vesta, that one used ion drive because it wanted to go into orbit around one, then come out of orbit and go into orbit around another. So that used ion drive. But for Cassini and for ExoMars, we're using chemical propulsion. So you basically give it a big boot from the Earth and on the rocket, and then just little tweaks to the orbital trajectory, which you don't have an engine going on all the time. So the difference with the ion drive is you can get to trajectories which chemical propulsion can't reach, and so but we don't need to use that for these particular missions. But in some cases, yes, it's part of the mission design. One there.
Hi, can you say anything about the possibility of habitable zones on moons further out, at Neptune, Uranus, and possibly even Pluto?
Yeah, so Pluto, certainly the New Horizons mission actually went past Pluto year before last and showed some fantastic data. So seeing Pluto for the first time, and it was remarkable there. We see there's a red coloration on both Pluto and Charon, which are to do with tholins. Now that's the same thing that we see with Cassini. Those really complex organic molecules are what's called tholins, and so those drift down onto the surface in the case of Titan and become dunes on the surface. And in the case of Pluto and Charon, it's actually sort of coming out of Pluto's atmosphere, because again it's a nitrogen and methane atmosphere. The same type of reactions can go on there, we think, and then deposit themselves on the surface. But yes, the subsurface oceans, there's a possibility of a subsurface ocean now on Pluto as well. There's also Triton and other moons in the outer solar system which are potentially locations for subsurface oceans. It's just that we haven't had the right type of mission yet to get the data from those. And so that, for the future, that will be, in fact, going to the Uranus and Neptune system. We've been involved in a number of proposals to try and do that, but that's a little way off in the current thinking. But there is a selection about to be announced at NASA, which may be quite interesting in this context. One there.
Thank you. Why is it that so many of these satellites of particularly Jupiter and Saturn seem to have these subsurface oceans, whereas there isn't anything like that on Mars or the Moon or the Earth?
Well, the Earth, of course, has water on its surface, and Mars did have water, and there's good signs that it did have water on the surface. The whole delivery mechanism for that water is open to debate. I mean, there's some which came at the formation of the solar system, there's some that came from comets or possibly asteroids, and so actually the Rosetta data seem to show that maybe a particular type of asteroid might be more likely than that particular type of comet which it went to. But water on the surface, and actually if you look at the amount of water in the system, at Earth it's relatively small compared to what there is at Europa and at Titan, and those moons and Enceladus as well. So those moons have a relatively large amount of water compared to what the Earth has now, and so this is something which is quite interesting. But they're beyond what's called the snow line, and so water effectively could freeze out. The reason it can stay in these subsurface oceans is effectively antifreeze. So there's some ammonia in it, which sort of keeps it in the liquid state underneath an icy crust. And in the case of Europa, as I say, there's sand at the bottom of it, and in the case of Enceladus, sand as well. In the other cases, it's ice. So it's ice sandwiching some water in between using antifreeze. So how it got there is a really good question, and one of the sort of big quests for planetary science. As, where did the water come from is certainly very important, but also could there be life anywhere else in the universe is the other really important question for us.
There's a lady in the front row here.
Are white smokers looked upon as the best bet for the origin of life?
White smokers and black smokers, to be honest, I'm not that expert in that field. You may well be right. Probably somebody else in the audience can answer better than I can. I mean, the point I was trying to make is that, of course, we've discovered these new regions where there can be life underneath the Earth's surface in those places which had previously been thought inhospitable. And so the fact that we're now detecting signs of subsea, that type of circulation happening underneath the sea, which gives the silicates coming out. This means that that type of thing could be going on at those moons as well. So this is the really exciting part of it. But, yes, and white and black smokers, I'm sure, are both very important. No. Oh, sorry. Yeah.
Hi. These are relatively longer time frames. How do you feel, or how do you see the Brexit overall, like impacting relationship within UK and the continent in the space agency affairs?
Brexit. Luckily, the European Space Agency is different from the EU. It actually predates the EU. These parts, the scientific parts of the ESA programs, European Space Agency programs, won't be affected by Brexit particularly. So there are parts which will be, some of the more commercial parts like satellite navigation and so on, which are a bit more affected, where Brexit may play a role. The EU in those cases, they're sort of driving the agenda. But for these, the science program, I'm lucky to say that we're not too affected. But it does affect research, of course, going on in the universities, and some of the research on these data are actually, will be affected by that type of thing. So the EU programs are very important for many people's research. There's one in the middle. 50-50.
Whenever whenever we're talking about the habitable zone, it seems like there's where conditions are right for life, as we know it.
Yeah.
So what are the potentials of looking beyond what we know and what we have already witnessed?
Yeah, well, very good question. I mean, there are lots of sort of chemical pathways which might lead to life of other types. But of course, the life we know about is the life right here. And so our best bet is sort of studying this type of life and how that can happen elsewhere. But, for example, on Titan, where we have that different chemistry going on with methane on the surface, I mean, people have, in science fiction particularly, looked at potential, for methane as being a way of making life happen. So we have a broad mind, but in terms of, and you can only make the measurements the ones which you actually take on the spacecraft. But our best bet, philosophically really, is we know so much, and there's much more to find out about life on Earth as well, including how it started exactly. There's some research at UCL going on about that. So in terms of life as we know it, that's our best bet in terms of looking for life elsewhere. So this is why we're looking for these essential elements and the liquid water playing a very important role. But people have postulated, yes, that Titan may be, but I think it would need another mission to do that.
Great. Maybe very last question, just a quick one.
With the matter coming off Enceladus in those plumes, is that mass permanently lost, or is it being gathered up again as it goes around the orbit?
Not much of it will be gathered up again. Yes, most of it is permanently lost. And so, just like with Mars, which has lost its atmosphere over the 3.8 billion years since losing its magnetic field, that's completely lost into space, into the solar wind in that case. And in Enceladus, it's lost into the system. It does, some of it ends up actually at Titan. We actually detected some of it at Titan. So some of the oxygen from Enceladus, or water from Enceladus, you can actually see all the way out to Titan. And that creates an interesting thing. If that could get to the surface, people have made some postulations about that. But yeah, it's basically lost to the object. And Enceladus would take some time, really more than the age of the solar system, to completely lose all its mass by that route.
So thank you very much for all those questions. And would you please join me in, once again, thanking our speaker for such an interesting talk.